Thanks, Moritz. So I won't talk anything about biology today, but I will talk about things that we've been doing a little bit more on the control side. And so when I was asked to give a talk, I thought about, obviously what should I talk about? And so I decided on the title before I decided on the content. So I decided I would give a talk on this title. And I'll say a little bit about why this came up and why this title and other things. So where did this talk come from? So obviously, as we all know, machine learning is kind of revolutionizing everything, and it's coming up all over the place. I've been working in a class of systems for a while now on safety critical systems, coming from aerospace, now a lot of things going on in self-driving cars and other things. And of course, we are also seeing machine learning getting applied to these systems. Controls and optimizations have already been applied to those systems. Now people are starting to put machine learning in. And I'll be frank, I'm worried. Right? I don't think machine learning is ready for these applications. I think there are problems that we need to solve, right? And so I'll tell you why I don't think we're ready, which won't surprise you maybe, but also a little bit about the context in which I think we have to fit these things in and work that needs to be done to do that. Because I'm not sure we're solving the right problems quite yet, to be honest. And so what do we need to do, right, to deploy machine learning in large scale, I'll say why large scale matters, safety critical systems. What are some of the problems we need to do? Okay, so what I will talk about first is to say, from the point of view of safety critical systems, and in some sense, taking an applications and industry point of view more than an academic point of view, how is this done, right? What's the processes, the engineering processes that we're going to need to fit into as a set of communities, right, if we actually want to get things to work? And in that context, what are some of the challenges to taking machine learning based approaches and integrating them into the way that we build safety critical systems? I'll say a little bit about some things that we've done, but frankly, most of this talk is not about the work that we've done, but rather about the work that I hope all of us will do going forward, especially you. I'm going to really talk about, here's what I wish other people were working on, much more so that I could use it and others could use it. All right, so that's the sort of setting. So a little bit of a different type talk, perhaps. Maybe that's what everybody's been talking about. So I won't say a lot about what we've been doing, but some. Okay, so I will motivate this from what I think is the scariest of application of machine learning right now, or one of the scariest. There are lots of scary ones, but one of them is self-driving cars. I was involved, many of you were also involved in the Darby Grand Challenge and other things now quite some time ago, 15 years ago. I'm still involved through consulting and through students going to work in this industry and other things. With these sorts of systems, so you'll recognize the Tesla over there on the left, right, which is maybe or maybe not a self-driving car, depending on how you interpret Autopilot. Coming across the top, there's a Waymo car, a Nutonomy car, another Waymo car. Anybody know the car on the right? What, pardon? John Deere? No. It's actually a car intended for urban driving. All right, that's a company called Zoox. So they are building a very different car from the ground up, right? And so it's an electrically driven car. Actually, if you saw recently, Cruise announced a new car that they've got that looks very similar to that one. It's basically a big box on wheels where doors open up and you get in and it takes you from point A to point B, right? So like a robo-taxi. All right, so the other thing I think is interesting about self-driving cars is that the language that's going on in these companies, right, and in the industry very much tracks a set of definitions that were put forward by the Society for Automotive Engineers in terms of levels of automation. So first off, how many people have heard about the SAE levels of autonomy? Raise your hand. Okay, about half of you. Okay, great. So just if you haven't, they're kind of useful conceptually to think about things because it is the way industry talks about it. Are we doing level 3, level 4, level 5 autonomy, right? So level 0 is easy, right? This is just you're driving your car, there's no automation whatsoever. Level 1 is driver assistance, so think of those things like anti-lock brakes or lane warning indicators or other things, right? You're in full control of the car, right? It's just that it's helping you do things. Level 2 is partial autonomy, so this might be cruise control, for example.
That's a clarifying question.
Sure, yeah.
So are anti-lock brakes 1 or 0?
I would say they are probably 1, right? But
that was just a matter of I'm not sure.
Yeah, and the reason is because they are, I would call them 1, and the reason is because they're taking a command from the driver and changing it, right? You're pushing full on the brake, right? And what it's doing is saying, I interpret that as brake as hard as I can, not start skidding my wheels, right? And so it's changing what you did, so it's some level of automation that's occurring. Same thing with traction control systems and things like that. All right, so level 2, partial automation, this would be things like cruise control, right? Where it now is controlling, especially the more advanced cruise control. It's not just regulating your speed, but holding distance between other vehicles and things like that, right? So still, you're in control, right? You're driving the car, right? Things like that. 3 is this kind of conditional automation, right? So I'll just read it. Driver is a necessity, but is not required to monitor the environment. The driver must be ready to take control of the vehicle at all times with notice. That's the definition that they put for level 3. This is a disaster, okay? Because, like, you're not required to pay attention, but you need to be able to take over whenever I say so, right? People don't work that way, right? You know, it's like, I don't have to pay attention? Fine. I'm going to read the paper. I'm going to go to sleep. I'm going to read my cell phone. Right? Oh, I got to take over, right? You know, what the hell, right? So, my opinion, level 3 is a disaster. Level 4 is high automation. Vehicles capable of performing all driving functions under certain conditions. The driver may have the option to control the vehicle, right? So here you're not saying I can do everything, but I got to tell you what I can do, and I can do the things I tell you I can do, right? So I can drive on clear roads, in sunny conditions, right? You know, with a car that's well maintained, right? You know, sort of all those things. Okay. And then level 5 is full automation, so vehicle is capable of performing all driving functions under all conditions. The driver may have the option to control the vehicle. But here, for example, there would be no situation in which the car could not do what a human could do, right? Whereas in 4, you're allowed to say, well, this car can't drive in parking lots, or this car doesn't know how to drive in snow, right? In level 5, it can do everything, right, that a human could do. So those are the levels of automation. And so, you know, the question is, where do these various things fit and which ones you can do? So, you know, these are already being done. Yeah, sorry.
Just a quick question. So which one of these is equivalent to autonomous driving?
Yeah, so I think most people say at the level that you get to 4, you're talking about autonomous driving. Some people say at the level of 3, maybe there's some autonomous driving, right? So another question would be, where do you put, say, Tesla's Autopilot, right? I mean, it's probably a level 3, right? Drivers, a necessity, but is not required to monitor. Well, they are sort of required, right? You know, so it's a level 2, level 3, right? They're not perfect, right? But you know, it will drive itself, right? To some extent. Yeah. Pardon?
Into dividers on it.
Sometimes, yeah.
I was just going to ask, where is like the auto parallel park type stuff? What is that?
Yeah, that's probably I think you could call that a level 4, right? It has a certain function that it can do, right? And it will do it with no, you know, you don't have to do anything. You press, right, the auto summons or whatever, or the auto park, or the self parking, right, parallel parking, right? Those are probably level 4 in a kind of simplified way. If you really, especially the ones where you're outside the vehicle, right? Because then clearly it's not level 3 because there's no way for you to kind of take control of the vehicle, I would say. And again, you know, they're not perfect, but I think they're good to discuss. All right, so 0 and 1, no problem. I think that 2, you know, is starting to get harder, right? And I'm not sure we can completely solve those things, right? I mean, these are things where the driver must be engaged and monitor the environment. Again, I would put autopilot here probably, right? That's what they intend, right? The problem is sometimes people treat it more like 3, right? Because, right, you stop paying attention. But they would tell you when you say okay, the contract that you're signing when you press okay says 2, right? You're responsible for the vehicle. You have to be able to take over at all times, right? You know, sort of this is an assist function, right? I think this one's impossible, as I've already kind of indicated. So that's a problem with the definitions. This is what most companies are trying to do, and I think it's really hard. And so from the point of view of what do we need to do, right, in control optimization and learning, if we want things to go into that particular safety critical system, I'd focus on level 4. And I think level 5 is probably impossible. And so I think it's just not, you know, all functions, et cetera, right, you know, sort of that's, you know, really hard. It's interesting to think about, you know, if you agree with those, whether you do or not, you know, how would you even convince yourself that the car could do this, right? And this question about certification is interesting, and I'll say more about it. I'll point out that we have a way of certifying cars right now, driving cars right now, human-driven cars right now. And that way of certifying human-driven cars is the car has to be safe, so it goes through a rigorous process, crash tests and all of that stuff. And then, right, the driver of that car takes a written test and a half-hour driving test, and then you are then certified to drive in all conditions, in all roads, right, in any country around the world, right, based on that. That's the way we do it, right? Amazing, right? Right, so 16-year-old, right, you know, basically gets their driver's license, they can go do any of those things. A question for us to think about is, is that enough, right? Should I take a self-driving car, take it out for a 30-minute test, right? Driver instructor says, well, why don't you turn left at this intersection up here? Okay, why don't you parallel park there? Okay, you're good to go. You can drive any place in the country, any place in the world, right? You're certified, right? That's what we do right now.
Is there a notion of automation where essentially the definition is something like car drives better than average human?
So I'll talk a little bit about what do we want the cars to do. It's not in here, right? But that's absolutely something people are thinking about. I'll say more about it.
The other thing that's not in here, and it's very important, right, is environment.
Yep. It is a little bit. So I'm not going into all of the details, but let me say, if you go one further level down, what they talk about are, they call them ODDs, operational driving domains. So they would say that in each of these you have to have an operational driving domain in which this can perform. Here the ODD is everything, but here the ODD, the operational driving domain, might be you're only allowed to drive on roads for which the traffic density is less than something or other, and it's a clear day, and you have all of the sensors working, right? You can define the ODD to more or less say, this is the set of conditions under which this car should perform correctly. And it needs to be able to detect its ODD. So it can say, wait a minute, I drove over here this morning, I ended up on some very crowded roads, right? And I can say, I'm sorry, I can't drive. I'm going to pull over. Driver, you have to take over, right? So that's the way they handled the environment, right? And so you have to define what environment you can drive in. Okay, so, as has sort of already been said, I think the challenge here is people are already doing some of this stuff and we're not ready. So people know about the crash that happened with an Uber car in Phoenix, right, where a self-driving car killed somebody, right? I mean, this car basically ran into somebody who was crossing the road. They weren't crossing at a crosswalk. It was crossing at night. There are all sorts of things, right? I think people looked at the video for this. If you watch the video that's online, what you'll see is it's dark, and then all of a sudden at the last minute you see this person in front of you, right? And then you say, I could never stop before I hit that person. I will also tell you, if you read the reports on this, the Uber car could absolutely detect it way better, right? Because it wasn't looking at the video image that you're seeing, right? It's got LiDAR and radar and all sorts of things. The bicycle that you see over there on the side, right?
For some clarification on that, if other people actually drove on the same road and used a different camera and it's perfectly visible.
Yep, right. So
They had a very darkened video that they released.
yes, right. So completely agree. And the vehicle didn't even try to stop, right? So it's not like it applied the brakes and couldn't stop quickly enough. It actually just fully ran into the person, right? So that's pretty bad, right? And safety driver want to pay attention. There were all sorts of other things. So that's one, as somebody already mentioned, right? Here's a Tesla Autopilot car, right? That somebody was paying close attention to what was going on, apparently, right? Obviously, right, was probably reading their cell phone or something else, and it ran it into a barrier, right? And so we are already testing things out. I mean, the Tesla's a deployed system, right? It's not like, I'm not saying it's using machine learning or not machine learning. I'm saying this is something you can go and do right now, legally, right? Is put this thing in Autopilot and run. So I'm worried because I'm not sure that we have a path forward to deploying these at larger scale. It's one thing to have, a couple of, 100 test cars out there with safety drivers in them, right? It's another to have 1% of the cars in the US doing these things, right? Okay, so I'm going to mainly talk about things that are relevant to what do we need to do to get high automation. How do we do this? And I think, and this already came up, one of the critical questions is going to be, how safe do these need to be, right? So how, we say they're safety critical. What does that mean, right? How do we think about that? And so one way to do that is to look for transportation systems at what's currently out there. And so human-driven cars in the US, there are about 7 deaths per billion miles driven. So there are 35,000 deaths per year in the United States, right? So that's a lot of billion miles driven, right? So you think a billion miles is a long way, but this is the large scale problem, right? When you're deploying these things, right, it's not like this thing's really good. It's driven, 25 million miles without an accident, right? Suppose. Great, right? You need to go billions of miles, right, with a very small number of accidents, right? So the failure rates have to be ridiculously small, right, in order to hit these sorts of numbers. So just humans driving already are only 7 deaths per billion miles, but that generates 35,000 people in the United States dying every year due to getting hit by a car, right, a human-driven car, right, of some sort. In the car, pedestrians, bicycles, all those things, right, so traffic accidents involving cars. All right, so maybe that's the best we can do, right? Maybe humans should be our benchmark, right? We should be as good as humans, right? And we say that's good enough. But if you listen to what the self-driving car companies are saying, one of the arguments is this will be safer, right? This technology will save lives, right? So we've got to beat that number. So can we beat that number? Well, if you look at rail systems, well, let's say rail, buses and rail, so right, that's another transportation mode. In fact, they're about a factor of 15 safer, right? So you're safer taking a bus or getting in a streetcar or something like that. Of course, they have bus lanes, they're bigger, right? If you get hit, you're probably not going to die, right? But also there's a professional driver there, right, in a bus, right, who's going to, know more. They're not going to be texting or not paying attention probably, right? They're going to get fired more quickly, right? All of those things. So we can certainly, in principle, it's possible. I mean, it's sort of physically possible to do better.
Does it include the deaths of people out of the train?
Yes. So this would be, something where an accident occurred involving a train or a bus and a person died, right? And typically, those are not going to be the people in the train, although occasionally, right? But rather the people that are outside. And then, I would say, in some sense, a gold standard, I don't know, the gold standard, is air travel. Right? So air travel is a factor of 100 times safer by miles traveled than driving. So any of you who are coming down from the Bay Area, you should absolutely not drive back. You should fly back if you're worried about your safety, right? Pollution and emittance and other things, we can have a different conversation, right? But it's 100 times safer to fly than it is to drive. And it's kind of crazy, right? Because to some extent, if something goes wrong at 35,000 feet, right? 250 to 450 people are going to probably die, right? Because the plane's going to fall out of the sky. You can't just sort of say, well, stop, right, and call AAA, right? I mean, it doesn't work that way, right? And so, but at the same time, right, it's just incredibly reliable, right? And I'll tell you a little bit more about how that reliability is obtained. Yeah.
You have neglected ecological damage.
Yes, I agree. These metrics are just around people, right? And so completely agree that from the point of view of the planet's health, right, as opposed to individual people's health, right, there's a different metric you could use. Although somebody actually, it was Sarah. Where's Sarah? Okay, so you did this analysis, right? Because she came down to visit us at CALTECH a couple of weeks ago, and she actually looked, right? So it was actually better to fly from San Francisco down to LA than it was to drive, pollutant-wise, right?
CO2 emissions.
CO2 emissions, right? So there you go.
Thank you, sir.
So I mean, I keep seeing this comparison by miles. I was curious, essentially, if you compare by, let's say, the time spent. Like,
Yeah, you can do all of those too. Well, it might, right? And again, I guess, you can do whichever metric you want, right? If you're going from here to Berkeley, I would argue that the miles is the right argument because, right, that's what the travel is, right? If you're sort of saying, look, I want to spend a certain amount of time in transportation systems, right, then maybe hours is the right argument, right? All right, so let me say just a little bit about, so how has aerospace, sort of gotten to this level? And it's a pretty sophisticated engineering approach, and I think one that as engineers, right, I think that the industry can be proud of. So how's this done? So first off, there are strong certification requirements that are in place. You don't get it to go just release a new plane or even a new software upgrade to a plane without going through things. We're seeing that in the 737 MAX things play out right now, right, where getting that back in, right, is having to go through a huge certification process that's getting in the way of putting it out there. And I can talk maybe over lunch if you care more about the 737 MAX, but I'll say a little bit about it. All right, so those certification requirements for software in aerospace systems are governed by something called DO 178C. This is basically the directive that the FAA uses to certify that you're allowed to put something in flight. And DO 178C defines a bunch of things. One of them is a set of categories of software. And so they have a hazard class and then the software level that you have to be at for that hazard class and then a failure rate per flight hour now, not per flight mile. And so level A software is software that, and it's software and hardware, so software system is software where if that software were to fail, human lives would be lost for sure, right? Plane's going to fall out of the sky. Level B is roughly, if that software to fail, you could get loss of human life, right? But it's not absolute that you'll get loss of human life, right? If the, a pilot doesn't take over in the right way, or you happen to be unlucky, right? Then maybe it'll happen, but it's not a guaranteed. Level C is major, typically not likely loss of human life, but maybe loss of the aircraft, right? So major kind of cost sorts of things. Minor is, the obvious thing, the entertainment system went out or something like that, right? Not affecting anything. And then, E is just no effect whatsoever, right? So the software fails, you don't even notice it, right? Yeah.
Yeah, I just want to point out a little bit of a misconception here. Because each crash of an aircraft consists of 100 deaths,
Yes.
the number is a little bit skewed because you have to have 2 orders of magnitude added. Now the hours,
Yes.
the catastrophic hours, are sort of the same exponent, but in reality, we actually have 2 orders of magnitude better.
Yes. So I would agree with you. And this is one of the things you got to be a little careful about. And again, it's the scale, right? You get all these factors of 10 that are in there, right? You fly 10 times, probably 100 times faster, right, than you drive, right? Depending if you're driving in downtown or not. But you fly faster so you get more miles per hour, right? You have more people so you get more deaths per mile or hour or whatever, right?
So what the point I'm trying to make is that these numbers are actually optimistic. The true expectation is at least 1 order of magnitude more, because when we drive the car, the autonomous driver does not control typically how many passengers are in that vehicle.
Yep.
And so that is actually much more stringent than 10 to the minus.
I agree. Even harder, right? Amazing that we sort of do this. So DO-178C defines these. It also defines the methods by which you can show this. So, how am I going to show this, right? I mean, this is a huge software system with it's a plane, right? It's that thing, right? So you got to show this for the plane, right? And so it's not like I can go and say, I have a proof, right? And the proof says, right, that, I put a bound on the uncertainty and the distribution, and I've computed all this out for all of those things, right? So it's much more empirical than that. And there is essentially here's how you do this, right? And you can do testing, you can use fleet data, you can say, look, these components fail at this rate because we've been flying them for 20 years and we know the rate at which they fail, and so we're going to use that rate of failure, right? And so there's a way of doing all of that. I would say the most common thing that you do in this is that you use some sort of fault tree analysis, right? And so you would say, okay, I've got some subsystem. This subsystem could fail if any one of these 3 things happened, right? This thing could happen only if all 3 of these things happen, right? So you kind of use and or logic, right? And then a little bit of statistics around that. And so you might say, for example, well, if I want this subsystem to have 10 to the minus 8th reliability, then the typical thing you do is if it's got any number of things, you just divide it by 10, right? There's only 3 of them, right? And you're going to sum these things up with some approximation about independence, right? But you kind of just, sort of say you want to be conservative for the reasons you just said, right? You don't want to accidentally, right, have it be higher. So you say, okay, well, we'll just put 10 to the minus 9 on all of these. And then if I have another one, I'd have to put 10 to the minus 10 on these 2, right? And sort of get up these numbers. If I have 3 that all have to happen, right? The left engine has to fail and the right engine has to fail and the auxiliary power unit has to fail in order for you not to have electrical power, right? Then I would say, okay, I need 10 to the minus 3 on each of these, right? Because all 3 of them would have to go out. And I've got to design my system to do that, right? So you basically go through and you do this type of analysis, and then I have to show you at this component level that I can achieve that, right? Well, now this is 1 in 1,000 hours, let's say. That might be something where I could just do the test. Right? I could run something for 1,000 hours, I could run 100 of them for 1,000 hours and collect statistics, or maybe they're out in the field or other things. So that's one thing you can do. If you look, what DO-178B, which was the thing that people were using up until about maybe 10 years ago, had one set, 2012. DO-178C allowed you to do things like formal methods, so you could prove things and try and use that as part of your evidence, right? We've proved that this piece of software will do the right thing. You could use model-based development. We've run simulations and shown in simulations that we believe. We validated those simulations, right? So there's all sorts of things that you can do to try and do that. But it is very empirical, right? A bunch of engineers have to say, here's how we've come up with the calculation. You have to defend that calculation, and then the FAA says, okay, we believe you, right? And so you sign off on that. One of them, by the way, for catastrophics, I'll insert a little bit of a 737 story. So one of them for catastrophic is, in a catastrophic, not only do you have to show this, but you have to show that there's no single point of failure, right? That there is no single component in the entire system that if that component were to fail, the system could, right, crash or whatever. So in the 737 MAX, right, there was a single point of failure. And most people who looked at it said, what the hell? How can you have, right, sort of one angle of attack indicator, right, fail and the aircraft fails? And the reason was it was the maneuver characteristic augmentation system. When it was originally proposed, right, it had a small amount of authority that it could do. It was intended to smooth out the flight and make it easier for the pilot. That was not considered to be a level A software. It was level B. No longer have to prove single point of failure, right? So it's okay to have a single point of failure. Why? Because the pilot could take over. is they're trained, right? And they know, and da-da-da, right? And the amount of authority changed over time, right? So you look at where these failures occur. I know a lot of people at Boeing, maybe there's somebody here from Boeing, they're an incredibly safety conscious company, right? I mean, the entire aerospace industry is incredibly safety conscious, but it's a big, right, sort of problem, right? You got thousands of engineers that are working on this, and how do you connect it all together and get it to work, right? And so there was multiple failures that occurred there, and one of them was that it was initially categorized as a level B software system, and then it effectively became level A, but didn't get reclassified, and so they didn't go back and make sure there's no single point of failure, roughly speaking. From what I know, and I'm not privy to the details. All right, but that's the type of thing that you would do in these systems to get these. Now, I'll point out just a couple of other things about this. So one is that these are very structured operating environments, right? So you're not on roads, right, with just people wandering around. You're in an airport, right? You're in the sky, right? You're in a sky corridor, or those things. So that kind of makes it easier in a certain sense. You have well-trained personnel, right? You have a pilot who has to go through training and other things, right? You have flight attendants who know how to do things. You have all of the stuff that you can rely on, right? It's not just you or me getting in there and sort of having our half hour. The driving instructor said I'm okay, right? A little bit more required. It's also the case that these are very expensive, right? About $1 million per passenger, roughly speaking, right, to build an aircraft. So you spend a lot of money on this, right? So we could maybe make self-driving cars that were this good, right? If you had to go through a 2-year training process in order to be allowed to sit in the driver's seat, and you had to pay $1 million per seat, so $4 million car, right? With a 2-year driving process, we could probably hit those levels of safety, right? I mean, so that's not going to happen, right? And so that's a challenge. All right, so just give you one little vignette to kind of show you the extreme that people take this, and people who've seen me talk before, I like this one. This is a flight, ZA002, so this is the 787 Dreamliner. So you may remember the 787 had some problems with the electrical system and other things. This was a little bit separate problem. And this is an article from 2010, so about 10 years ago now, and the title is, right, Dreamliner Fire and Smoke Details. So this is when they were not yet releasing it, they were doing test flights. And if you read through the text on this, and you can find it online, it says that there was a loss of primary electrical power at some point. It was actually about 10 minutes out from landing, so you're coming in for landing, right? And something went wrong, and the electrical power in the aircraft went out. Right? This is a modern aircraft. That means you're the pilot, right? It goes dark. The cockpit, all of the displays turn off, right? Sort of the whole cockpit goes dark. You are now flying open loop, literally. The engines are still running, right? You're getting propelled through the air, right? Nothing you can do, right? I mean, it's just moving, right? And so it went dark. That's bad. And so if you read on, it says that the ram air turbine deployed, right? So what's the ram air turbine? So on the bottom of every commercial aircraft, modern commercial aircraft, there's something called a ram air turbine. It's basically something that sits up underneath the fuselage. If primary electrical power goes out or primary hydraulic power goes out, because there's a lot of hydraulic power for powering flaps and stuff, this thing drops down into the airstream. What it is it's a prop with 2 things connected to it, an electric generator and a hydraulic pump. And they go through an entirely separate set of circuits to everything that's required to fly the aircraft, right? The flight control system, essentially. Your entertainment system's still down, right? But this thing comes up. So the rat deployed 10 minutes out from landing. This thing goes down, starts spinning up, everything comes back up, and they successfully land the plane, right? Amazing, right? But it's not amazing, right? Some engineer someplace said, geez, right? I've only got a 10 to the minus 8th probability someplace, right? That the electrical power might come out. It was a short in an electrical cabinet, right? That's supposed to be redundant and backup, et cetera. But they, the probability, so somebody went and thought, boy, we better make sure there's some fail-safe in there, right, that does this. And my question to the machine learning community is, what's your fail-safe, right? Because this is what we're gonna have to do, right, if we want to get this stuff to work.
Richard,
Yeah.
that's standard. That's not 787 then.
Oh, this is standard on almost all modern commercial aircraft.
So it wasn't that they actually anticipated.
No, not this thing, et cetera. It's always there. All right, so just to give you some sense about the statistics on this, there are about 100,000 flights daily, so about 35 million flights per year. There are 6 documented rapid deployments that I was able to find in the last 20 years. 6. Let's suppose it's 10 times that many, right? So there would be 3 per year. So 1 in every 10 million flights the rat has to deploy, and it sure as hell better work. So if you actually go, there's a place at United Technologies Aerospace Systems, now Collins Aerospace, and if you go to where they make these things, they actually have a poster that shows every flight on which the rat deployed, and it lists all of the passengers on that flight, because all of those people's lives, right, were saved because of the system they're building at that place. right? And it's not a whole bunch of posters, right? Because there's not that many of these that are happening. So this is one of the, and it better work, right? One every, right, sort of 3 years, right? Or 3 times a year, right? 10 million flights, this thing pops out, it's got to work. So that's what that group thinks about. And so the point is just, aerospace has thought about this a lot, right? And how do we make these things safe? And many of you will get on a plane and you will assume that you're going to get there, and it's a really good assumption, right? Probably most of us don't know anybody who died on a plane. Probably most of us know somebody who died or almost died in a car accident or something similar, right? Because it's 100 times safer. So I think that's the kind of attitude that we have to take. And I'll point, this is something that requires continuous progress. So here's a curve of airliner accidents per million flights. You had a different unit, right? Number of flights, not number of hours, not number of miles, right? But you just see this decreasing trend from 40 years ago, right, to, I don't know what it is, about 0.3 today, right? So about a factor of 15 or so sort of increase. And so it's just a continuous process. Every time something happens, what do we do to make that not happen again, right? Over and over and over again, right? And in the earlier history, sort of before this chart, it was in fact failures of the sort that we're seeing in self-driving cars, perhaps, right, that caused the government to put into place these regulations, right? People were going up in airplanes and the airplanes were falling out of the sky, right? And the public demanded that the government do something about this, right? And so I think that's going to happen here as well. Now, this is harder for self-driving cars. First off, we're already at a pretty low accident rate. You go back to the beginning of the aerospace industry, there wasn't an airplane, right? There was nothing to compare it to, I suppose walking or something like that. But if you were sending mail across the country, right, then that was the only way you could do it. We already have only 7 deaths per billion, right? So we clearly have to do that well. I can't make it 10 times worse, right? So I know what my floor is. Improvement is slow, right? So a 10 or 15x improvement took 40 years, right? Can we wait 40 years? If you're an investor in a self-driving car company and you say, well, we'll get the rate down to better than humans in 40 years, do you invest in that company? Right? And the numbers are scary, again, the large scale. If 1% of the cars deployed were self-driving cars, right, that's about the same deployment we have of electric vehicles in the state of California, right, 1 to 2%. Then there would be, right, 35,000 per year, 1%, 350 deaths per year. That means every day you would read in the paper, right, that a self-driving car killed somebody, right? I don't think the industry could survive that, right? So we got to do better than that. All right, so, and the economies of scale are different. All right, so let me just say a couple more things about this. Yeah, I managed to get to slide 5, so Maritz is kind of going, oh shit, right, he's got 12 slides, it may take him a while. Oh, sorry, did that get recorded? All right. So if you look at what's inside a self-driving car, lots of other systems, right, you'll see this kind of complex stack of things, right? So you've got low-level controls, you've got trajectory generation of various sorts, right, MPC and other things, and you have some high-level decision-making, other things that are going on. And of course, as has already come up, the environment interacts with all of these levels, right? There's the sort of physical environment interaction, but there's also, right, the logical environment interaction. Is it my turn to turn? Is somebody else turning, right? It's all of that stuff going on. We have lots of communication infrastructure and other things that enables us to interconnect and make much more complicated control systems. And in particular, typically now you won't see one kind of algorithm running on each of these blocks, but you'll see many algorithms running, right, in parallel, right, and choosing whichever one works. When you do that, you might now have hundreds of independent threads of execution within all of the computers that are running, so you now have timing issues between all these things. What if one part of the system sees something before or after another part? Do they behave consistently as that goes through? In addition, the models that we've typically used for offline design are now being used for online design, right? You're learning what's going on and using that. And so that makes things more complicated. And then you're talking all of the stuff that's offboard, right? All the cloud computing resources and other systems and all of those things. So it's a very nicely complicated system that engineers are dealing with. And we have to think about how we manage that complexity. And so I'll say a little bit more about it, but one of the things we do is that we split it up in layers, right? So you're a low-level feedback control person, or you're a planning person, right? Or you're a kind of logic person, supervisory person up at that top. We also divide it by domains. So you are perhaps somebody who thinks about the sensing side, and kind of machine learning might fit more over there, or you're somebody who thinks about more the actuation and control side, planning, robotics, and all those things. And in my experience, a lot of the errors that occur between these domains, right? I thought that, I was going to supply it this way. I didn't know that you were going to treat it that way, right? And that's where you get all your errors, and that's why it takes so long to see these, kind of weed these things out. All right, so we can think about it whether there are ways to deal with that. There are lots of examples where this comes up. Aerospace system, autonomous systems, but also factory automation, smart buildings, other things, maybe less sensitive, right, safety critical in that context. And there are lots of challenges. How do we define the layers and interfaces? How do we scale them? How do we think about safety, robustness, security, and privacy? And all of these things matter too. And so it's hard. And the other thing that's happening is, and again, the purpose of this workshop is that now, a lot of places, the advances in technology are making a huge difference. So for example, optimization is an enabler, right? Receding horizon control and other things work because we can do real-time optimization, right? And so we're using those things in these sorts of systems. Machine learning, similarly, right, is going to hit all of these things, right? Because there's no question, I think, that at the level of sort of state estimation and other things, we're going to use deep neural networks, particle filters, and other things to classify and predict, right, where the traffic's going to move, right, and what I'm going to do and how I'm going to interact with that. So I think all of those things become very difficult. I'm going to focus just on these safety critical ones at the top. All right, so I want to just say a couple of things about now where are the problems I think we should look at and what perspective can we take. So I want to talk about what I think some of the challenges are, again, from this perspective of large-scale distributed safety-critical systems, and then a little bit about what controls people would sort of, how we would approach it, at least I would approach it. And I put these as easy problems in the sense that these are probably, we all know these are problems, doesn't mean they're solved, but they're sort of the easy part of it. So first off, the failure rates have to be a lot better, right? As has already been pointed out, right, even 1 in 1,000 is probably not the real failure rate you want 10 times better than that, right? So I think it's great that we're now able to do ImageNet and other things at 90%, right? Great, right? That's 10 to the minus 1, right? Okay, I'm going to have a lot of those running, right, to get me to 10 to the minus 9, right? And the question also is, what's the failure, right? Is that 10 to the minus 1 per frame? Well, how many frames do I see in an hour? A lot of frames, right? So you see 10,000 frames in an hour. So if I go for 1 billion hours, right, how many frames do I have to get correctly, right? And this is a huge problem. So how do we get those really, really, really small, or know that they're off and do something different, right? I also think that just classification error is not the one, right? We want something where we say, look, it matters how far I'm off, right? There's got to be some metric besides just yes or no, right? So, of course, what we would do on the control side is that we understand things about stability margins and uncertainty balls, right? And you try and get things that you say, look, here's some measure of how far away I am from the desired performance, and I want to prove something that says as long as it went within some ball, right, I will guarantee that the system operates safely, right? Can we do something similar on the machine learning side where we start talking about bounds on error? What do we mean by error? How does that error translate through? What types of uncertainty should we have? How do we take into account temporal things? And so I've drawn this picture down at the bottom that's sort of the standard controls diagram, where we have some specification that says I want the attenuation between the disturbances that are coming in, think about that as wind or something else, and the outputs that I care about, think about that as the tracking error, to be bounded, right? And I want that to be true for all uncertainty models. So think of this as a dynamical model with some bound on the linear input, linear output response, and I want it to be true for everything, right, within that bound. So what would this look like for machine learning, right? So can I say something? I say I've got a classifier, right? And I want the classifier to work, right, for all bounded disturbances, right? So this would be all of the various things I could see in the environment, and unknown dynamics, right? Because I'm moving around, the other cars are moving around, there's lots of things going on. Can we make that statement? I don't know how much data is required, and it would be nice to know more, right? So if I say, how much data do I have to take on self-driving cars to convince myself, right, that I get less than 7 deaths per billion miles? I think Waymo's driven the furthest right now. They've driven about 25 million miles. Okay, that's definitely not enough, right? I saw someplace just a title of a paper that said, if you want self-driving cars to be tested out, you need to drive 30 billion miles, right, to get the human level of accuracy, right? We need 30 billion miles worth of driving. And of course, the problem is corner cases, right? There's just all sorts of, right? You need 30 billion miles of driving to see all the weird corner cases that are going to come up, right, somehow, right? Or you need to put a bound on it, right, and say that corner case will somehow not drive me out of that bound. So of course, what we do on the control side is we use, kind of model-based parametric representations of things, right? So we know how much data we need to take. We're going to put them into parameters, right? It's a very structured problem, and we try and reason over worst-case behavior, right? So we say, for this model, which I know is not correct, but it's got some bound around it, right? I can show you that will always work. The control system will always maintain stability. I think that we have to be careful about thinking about the output of the errors, right, not the errors themselves, right? The question is, do we run into somebody, not did I classify that as a person, scooter, bicycle, or car, right? I could be wrong in the classification and still take the right action, right? So how do we think about, right, how do we map it through to action, right, rather than just thinking about the error at the front part? There's another, and we know we need to do that because the system can react to things. And so, of course, on the control side, we do a lot of that, right? What we care about is not what was the error that happened from this part or this part or this part, but what was the error through the system in closed loop with everything running, right? And so maybe there's some lessons to take there. All right, and then just the last challenge is, of the easy ones, right? Again, this kind of early adoption. I'm worried that we are starting to see people make use of machine learning. All the self-driving car companies that I know about are all using machine learning inside their systems, right? And yet, right, it's pretty, it's great. I mean, I don't know how else to solve the problem, right? But I also don't think that the safety levels are up to where we're ready for it. So maybe we have to use machine learning for performance, but optimization control, things we're more comfortable with for safety, right? Because I don't have to classify something in order to know that there's something in front of me and I need to stop, right? So maybe we can do something there. All right, those are the easy problems. What about hard problems? All right, so for this one, so Emilio Frazzoli's coming to give a talk at CALTECH next week, and I got his abstract yesterday, and I said, he got it, this is it. So I'm going to use Emilio's version of what the hard problems are, right? So this is from Emilio's abstract that he sent out. So he said, right, not me, right, that we've moved past the peak of the hype cycle, right, in self-driving cars, and the industry is now bracing for a development timeline that's much longer than earlier predictions. Very true. People were going to have this out in 2020 or 2021. Now people are pushing out to 2022 and other things.
2020. Anybody says 2021, you have to say, stop it. You said 2020.
Yeah, right. Exactly. Right.
And
So
we're here.
right. Exactly. And where are they? Right. So, but industry's recognizing this is a harder problem. Furthermore, Emilio argues that in fact, figuring out the fundamental issues is going to require a concerted effort by industry, academia, and regulatory bodies. Right. So I think one of the things we ought to think about is, right, well, okay, we represent the academic side and maybe the industry side, we have to start engaging the regulatory bodies, right, in all of this. That's hard and takes work. Berkeley's a great place to do it. You got a, Institute for Transportation Studies, right, that talks to the government, right? So, we should leverage that. Other universities, I'm sure, as well. And then he says, the issues that arise go beyond the very hard, but in some sense standard and well studied, that was my easy, problems of control, perception, et cetera, right? So that was the previous slide. But where we have to make decisions is how we want these vehicles to behave, both at the individual single car level and the fleet level. And again, think about the fact that if you have thousands of these things out there driving hundreds of thousands of miles, you've got to worry about these really low statistics. How do we deal with interacting with pedestrians, cyclists, other cars, all of those things? And so, we have this picture that, as has already come up, we've got an environment, right? It's got cars and people, and we have to reason about all of these things. But we all know that, the reality looks a lot more complicated than that, right? I mean, people don't walk in straight lines and stay in the crosswalks and other things. I mean, this is sped up, but, there's, I'm sure, jaywalkers in here and cars that sort of stop and break the rule and go through the red light and all that stuff. And still, society's expectation is that these need to be safer, right, than they are with humans driving them. So how in the world are we going to do that? And how do you certify that? I mean, maybe I can say for this particular intersection, right, which is the intersection of 3rd and Howard in San Francisco, I can drive here, right? Because I've taken enough data and I can actually do that. But then, can I drive anywhere else? So this is an interesting little place in Norrköping, Sweden. It's a town square, an intersection, in which there are no traffic indicators. None. It's just some roads come in, people are walking around, they're bicycles. There's nothing, right? There's a sign coming up saying, uncontrolled intersection ahead. They actually did it as an experiment in kind of urban interaction and other things, right? So how would people interact, et cetera, right? I don't know what the death rate is there, right? But, hopefully not too bad.
The problem is they're Swedes.
Yeah, maybe that's what it is, right? All right, so but you can sort of watch what goes on, right? So this is just a video that's posted online of this, right? You see, it's not that crowded, right? So maybe it's not that bad. People walking around. Here's a doubly parked vehicle sitting there. Here's a car coming up, right, on this particular intersection. Car slows down. There's another car coming. I guess he saw him. Here's another car coming, right? There was, did they get to go? Did I get to go? Right? I don't know, right? So we thought a little bit about this problem, and then Maritz, I'll stop in a second, in the context of not driving but walking. Right? And so my last little vignette about this is some work we did with Andreas Karlo, who's here, and Pete Troutman, who's a PhD student at CALTECH. And we wanted to understand navigation in crowds. And so this not very good picture is the CALTECH cafeteria from above. So for those of you who visited Chandler, this is a part of Chandler, a bunch of people that are around here. And the question was, could we get a robot to walk through at the busiest time of day, right? Which is lunch. And of course, the problem is that if you do a sort of simple prediction and you say, well, here's one on an intersection, here's all these people, I don't know which way they're going to go, right? I get some expanding set of places they might go. And if I'm this person here that's coming in, right, I can't go anywhere, right? Because I don't know, people might walk in front of me, right? And so you would just say, don't move, right? So Pete called this the freezing robot problem, right? Because you do a prediction, you put some uncertainty bounds around it, and you see that there's no place I can go without the possibility of being hit. But that's not the way it works, right? Because if you go there, right, people will move out of your way, probably, right? And so, right, you have a situation that maybe looks a little bit more like this. If I just look at what happens, I'd say I'd run in, but I have a whole bunch of things they might do, and I might say, you know, it's more probable they'll choose the paths that veer away from me if I go right down the middle of them, right? And so he came up with a way of sort of characterizing that in terms of interacting Gaussian processes, right? So he just assigned a probability to every path, right? Every collection of paths, and sort of did all of that. And so, you know, I think there are techniques, and then he implemented it, right? So then he went and he implemented it in the Chandler Dining Hall. The robot's down here. And so this robot, right, there's somebody talking, obviously not paying attention. The robot's trying to get over there. This guy just about backs into him, right? But we were able to Pete was able to get this thing running, right? And not run into anybody and get from point A to point B, right? And it's more or less what you would expect, right? Somebody's coming this way, you're going this way. If I'm going to get there before, the chances are they'll slow down. Or two people are coming this way, if I go right in the middle, chances are they'll spread out, right?
But how many times did he do this?
Yeah, right. So we had thousands of hours of video, right? Ooh, thousands, right? You know, that's not much, right? So, but also the consequences were small. It wasn't a safety critical system, right? All right, but I'll use it to illustrate another little piece, and then I'll stop, which is, this is what the actual robot looked like. Sorry, this is not so great, but so here's a little Pioneer robot with a superstructure on top of it. And initially we just had the superstructure. We had to put a hat on top of it because the problem was people didn't perceive it as a human. So when we put the hat on top of it, they like clicked in people's minds, oh, that's something that, you know, I should treat like a human somehow, right? You know, because it got a hat, I don't know. So, and it would say where it was going. I'm going to get pizza, right, or whatever it was. And then it would go roaming around. And so I'm going to show you a video. So what you're looking at is kind of a full video. Up here you're going to see some tracking points and other things. Eventually the green dots will be the robots here. You see the hat. We're tracking people's heads. The robot's trying to get across this area. And so there's a little bit of registration error here, just in the way that he did the video. So you'll see some green paths eventually that sort of start offset from the robot. And the paths, these red paths are where the humans are. But I think I want you to look down at the bottom of this. This is just the overhead view, and sort of see what happens. So the robot's sitting here. It wants to go this way to the right. And so it's sitting there and sort of doing that. And then the student walks up and sees the robot and stands in front of it. And then the robot turns to turn out of the way. So the person moves and stands in front of it. And tries to go the other way around it. So the person moves and stands in front of it. This was not in our database, right? This behavior doesn't happen to humans because you punch the person in the face and say, hey, man, what are you doing? Get out of my way, right? So that's another question, right? Which is, how is it that we're going to interact with, right, self-driving cars? Oh, that's a self-driving car. It has to stop. Just cut in front of it. Don't worry about it. Ooh, not so good if you did machine learning, right? And all your behaviors were based on, right, human-driven cars, which you probably say, that person's not paying attention. Whatever you do, don't step in front of them, right? So I think that's something else that we have to think about. Okay, so that's sort of all I wanted to say, right? I haven't told you anything about what we've done in our work beyond this, right? And this is somewhat old work, so this is from about 5 years ago, 6 years ago now. But I think that it's a sort of wonderful area for thinking about because we do have these sort of very complicated systems that we are trying to think about. And we have to think about, how do I do that in a way that is, how do I do that in a way where I say, look, if I want to get from what humans can do to what we can do as engineers, right? How do I get there? And can I take some of the lessons of what we've done over here, which don't involve machine learning, for example, at all, and only involve optimization sort of recently? Can I take those lessons back, right? I don't know, but I think we need to think about things that look like the processes by which these are going to get certified and how we fit into those processes and what math is required. And these are mathy things down here, right? So it's not that math isn't allowed, right? Math is allowed, but you got to actually have the math be useful. Okay, so I'll sort of leave you with that. I'm here the rest of the day. I apologize I can't be here tomorrow, but I'm happy to talk more about it now, at lunch, all afternoon, whenever you like. So I'll stop there. Thank you.